Okay, I guess you heard. Yeah. Before I start with my talk, I would like to first share a bit about myself. So I've been working on 3D reconstruction and generation ever since my PhD in 2018, where I mainly worked on self-supervised 3D reconstruction and appearance modeling. And between now and then, things have moved very fast. So I joined Google in 2022, where I then worked on generative 3D reconstruction, as well as generative 3D relighting, before video models changed the research landscape and what is possible. And the progress in our field has been so fast and impressive that 3D reconstruction methods with the help of generative AI actually work at scale. So our team at Google was able to convert some of that research into product. So first, we focused on reconstructing shoes, where we used image models to help with 3D reconstruction and landed it on Google Shopping. And then later, we started to work on video models, which helped us to expand to any kind of object category on Google Shopping. And the progress in our field over the last couple of years has been incredibly exciting. And in today's talk, I will be discussing 3D generation methods and how to put them into perspective with generative video models. But first, let's define what a generative 3D model is. So at its core, it's a system that takes as input a control, like a text prompt or an image, and it uses a generative model to produce a 3D representation. However, to actually see the content on the screen of a 3D model, it must be rendered into 2D images so we can actually look at them. And early works on generative 3D modeling used GANs in 2016, where we had a pure generative model with a noisy latent that was then trained to produce 3D voxels with a 3D discriminator. And here we had no specific control over the inputs and needed 3D ground truth data for training. And some follow-up works, like Platonic GAN, addressed the 3D data problem by removing the need for 3D ground truth by adding a differentiable renderer and a 2D discriminator. And this allowed to train models directly on 2D internet data, and Platonic GAN also introduced an image encoder to enable 3D reconstruction from single images. And building on the idea of image-based reconstruction, works like PixelNerve focused on multi-view inputs. And the core innovation here was to aggregate encodings from multiple input images, fusing them into a single, consistent 3D representation in the form of a nerve. And now all of these methods I've mentioned have something in common, like they all directly predict a consistent, explicit 3D representation. And this has a significant advantage because once you have that 3D model, you can render the model from any view, which is very fast and cheap. And this makes it perfectly viable for real-time applications on mobile devices like phones and tablets. But the downside is that the overall quality of those results is quite low. So maybe we should ask ourselves, well, why is the quality low? And if we recall Sutton's bitter lesson, the answer might lie in two limiting assumptions. So first, high-quality 3D data is very scarce. And secondly, that we shouldn't use any strong inductive biases, like in our case, rendering. But if, on the other hand, we look at 2D generative models, like image or video models, we realize that those models actually scale with data, since we have billions of 2D images or videos on the internet. And furthermore, these models have limited inductive biases, since they directly produce 2D pixels. So over the years, these models have been becoming better and better, since we have more and more compute. And so, yeah, we can train them on bigger models with bigger compute. But the question is, do those video models produce realistic and also, more importantly, physically correct outputs? And in one of our recent works, we were interested in exploring this direction and wanted to see how well do video models understand 3D. To answer this question, we investigated a video model's knowledge to understand the pose. So here, as you can see, for two images A and B of a scene with very little overlap, we ran an off-the-shelf pose model, such as Duster, to predict camera poses. And we know that off-the-shelf pose estimators that rely on visual correspondences struggle to accurately predict the pose. So to find out whether video models can understand the pose between 2D images, we used several video generation models to interpolate a video connecting the two images. So assuming that the video model can understand the pose between two images, it should generate a physically correct path between both of the input images. And to verify this, we feed the additionally generated images along with the two input images to this off-the-shelf pose estimator and check if the pose estimator improves. And we found that this is actually the case, and these additionally generated frames from the video model actually enhance the pose estimators. And as a result, this means that video models are capable of actually implicitly modeling the physical world correctly. So if we look at video models, or like if I look at the latest video models, we can convince ourselves that these models produce highly realistic results. So for instance, here, this video here was produced by the Veo 3 model, which shows us the diverse camera motion, scene motion, as well as highly realistic physics. And furthermore, interactive video models like Genie 3 already allow us to navigate 3D worlds. So as you can see here, we're not just watching a clip, but we can actually actively navigate through a classroom. So here, each keystroke, like forward, turn left, turn right, prompts the model to generate new frames. And we can freely navigate and inspect different viewpoints and eventually walk towards the window and look outside. And here is the critical part. When we turn back, the classroom looks the same as before, and it actually remains consistent. So the question becomes, why do we even need to explicitly model 3D? If those purely 2D video models are already this good, what's the argument for explicitly modeling 3D? And the answer is, well, while those video models scale with data and compute, the inference cost also goes up, which prevents us from serving these models on phones and tablets currently. So how do we overcome this issue? And if we look at this point from a 3D perspective, we already know tools like Nerve that can model 3D content given hundreds of images. So once we have hundreds of images, we can capture 3D scenes in great detail, which then allows us to render arbitrary novel viewpoints. And this can be achieved at a very low cost compared to image and video models. So let's look at an example. So here is a fly-through of a large complex scene, and it's a house with multiple rooms and a large garden. And what's important here is that this is actually fully interactive, which means we can control the camera arbitrarily and choose any viewpoint we want. However, this scene was generated by manually capturing many images of this house from a diverse set of views. So, but the good thing is that it seems like we have two pieces of a puzzle that we can combine. So on one side, we have generative image and video models that produce highly realistic 2D images. And on the other side, there is Nerve models that can distill those images into an efficient 3D representation that can be served and rendered efficiently. And this is exactly the combination that we explored in CAD3D. So CAD3 is a method that can take in a text prompt, a single image or multiple images, and generate 3D scenes. So let's have a look at this method in more detail. So CAD3 first takes as input observed views, which contain an input image and the corresponding camera parameters. And we then encode the image using a pre-trained VAE into image latents. And while the pose and the camera information is encoded into a per pixel ray coordinate map, which basically just contains each pixel's ray informations. So simply, it just contains like the origin and the direction per pixel. And the model also takes in novel views. And for those views, we don't actually have an input image. So we pass in noisy latents instead of encoded latents to the model, as well as the pose information. And to help distinguish between the observed and the novel views, we also feed in a mask that tells the model which views are observed and which views are not. So the input to the model can be any mixture of these two different types of inputs. And they're treated exactly the same by the model. So it's just a large set of views that may be known or unknown to the model. And so the model takes all of this information in and then simply produces a set of generated null views for the specified target views. And we train this on a large set of pose multi-view images, so it's supervised to produce multiple consistent frames at once. And so because this model has a tension between all of the different frames, we can actually get really consistent samples. So once our diffusion model is trained, we then proposed a two-stage setup to reconstruct the results. So here, given some input views, we use the multi-view model to generate a dense set of views of the desired scene, as you can see here. And then we simply reconstruct those views using a relatively standard nerve pipeline. And while the samples that we generated are not entirely 3D consistent, they're consistent enough that the nerve reconstruction pipeline is able to consolidate them into a consistent 3D output. And end-to-end, our method is able to produce full 3D scenes in as little as 1 minute from any number of inputs, like 3 images or even just a single image. So if we go back to our overview, we see that we can use 3D methods like NERF to combine generative 2D models to generate 3D models that are fast and cheap to render. However, having an optimization step in this loop is still a bottleneck for the inference speed, and we asked ourselves, well, can we replace this optimization step with a feed-forward model? And the answer to that question is given in another work, which is called Bolt3D. And Bolt3D lets you generate 3D scenes in less than 7 seconds on a single GPU. So let's have a look how we achieve this. The key idea here is based on splatter images, where the goal is to reconstruct per pixel Gaussian splats given a single image. However, this method was a purely reconstruction-based method and couldn't handle any unseen parts of the scene since it wasn't a generative model. But however, in Bolt3D we proposed to also in Bolt3D we proposed to also represent the 3D scene as splatter images, but instead of a reconstruction model, we proposed a generative model. And compared to splatter images, Bolt3D allows us for hallucinating unseen regions of the scene, since we're actually proposing a generative model. And in Bolt3D, the generation process consists of 2 parts. So first, we have a latent diffusion model that generates multi-view appearance and geometry in the form of images and point maps. And if we go back to Cat3D, for Cat3D, we only predicted RGB latents, and here we additionally have point map latents. And then in the second part, a Gaussian head then jointly regresses the remaining properties of the 3D Gaussians, namely the scale and the opacities, given the images and the point maps. And the output of the Gaussians are multi-view splatter images, which hold 3D Gaussians that then together represent an entire 3D scene. And the reason for this two-stage pipeline to first generate RGB colors and XYZ positions, which is then followed by predicting opacities and scales, is that we can robustly obtain supervision for both the appearance and point maps from multi-view data sets. And for obtaining supervision for positions, we simply run structure for motion pipelines on existing multi-view data sets, which are pretty robust. However, it's not actually trivial to obtain good quality supervision for opacities and scales of pixel and Gaussians. So it's not easy to train a diffusion model to output them. And on top of that, a recent work showed that given colors and position information, it's much easier to regress opacities and scales than to generate them. And this explains our design choice to first train a generative model of RGB and XYZ, which is then followed by regressing the remaining properties. So let's have a closer look at how we do this. The generation process is implemented using a multi-view latent diffusion model of appearance and geometry. And then the inputted model, similar to Cat3D, is a set of seen and unseen views of the scene. And the observed views contain a clean RGB latent, and this time also a noisy geometry latent and a camera pose of the observed view. And the unobserved views contain a noisy RGB latent, a noisy geometry latent, and the camera pose of the target view. So compared to Cat3D, here we additionally have like geometry latents for both the unseen and seen views. And then the diffusion model outputs a set of clean image and geometry latents, and it does it by for each pair, one pair for each view. Sorry, yeah. And then the image and the geometry are then decoded independently to full resolution RGB and XYZ images. And an insight here is that simply autoencoding point maps using off-the-shelf RGB autoencoders results in very low quality reconstructions. And I'm not going to go into detail right now, but we will talk about the geometry autoencoder later. So next, we then train so once we have this, we train a multi-view Gaussian head that takes in all of the predicted per view point maps and RGB images to produce a set of splatter images. That means we transform each view into Gaussians. And here it was important to have cross-attention between all of the views so that the network could reason about all the splatter images together to ensure 3D consistency. And then finally, we can render these splatter images to view our final output. And to train this model, we created a large data set of 3D scenes. And we ran master, a recent 3D structure for motion pipeline on all scenes from CO3D, RA10K, MV ImageNet, and DL3DV. And this was necessary so that all of our data has dense XYZ notations for every image, making this data then suitable for diffusion model training. And together with synthetic object data sets, this allowed us to train our generator on a large scale data set. So let's have a look at some of our results. So here we see two scenes that were faithfully reconstructed by just a single image. And we can also see that the model here can actually hallucinate unseen regions. And we also have more examples on our project webpage. There's even an interactive viewer where you can explore our scenes in real time. So please take a look yourself. But one thing that I would like now to talk about now in more detail is this geometry autoencoder, because learning to output a geometry with a latent diffusion model has proven surprisingly difficult initially. So we found that VAEs pre-trained for image autoencoding were not really appropriate for autoencoding geometry. And we found this to be the case regardless of this scale of the scene, but I actually observed that for bigger scenes, we get even more catastrophic failures, yeah. And this is likely because the objectives for compressing images are not really appropriate for compressing geometry. For example, perceptual losses don't really make sense for geometry. And another reason is the scale of the data, because input images are always within 0 and 1, but this is rarely the case for geometry. And something else interesting, or like another interesting insight that I would like to share is that we found that the decoder in the VAE for XYZ data actually needs to be a transformer. Even though so it should be a transformer, even though quantitatively, a convolutional decoder performed similar to a transformer decoder. But when you actually look at the convolutional decoder, or like the results of the convolutional decoder, it leads to perceptually jarring artifacts, like not actually maintaining straight lines, as you can see here on this slide. And this can also be seen, like those artifacts can be seen across a big range of scenes, including those bathroom shelves here. So, and since fine-tuning geometry VAEs for both 3D was quite crucial, I would also like to share another line of work in the VAE space with you. And this is actually something that we recently submitted to CVPR. So you're actually the first to hear about this work, and since it's still under review. So let's take a quick detour into the VAE land, and then we're going to get back to generative 3D again. So the paper I'm going to present is called Vision Language Models as Perceptual Judges for Human-Aligned Image Compression. So usually when we train autoencoders, we use losses such as PSNR or SSIM. However, these losses really poorly align with human perception. So for instance, humans are very sensitive to perturbations to faces and text, but less so to natural textures such as grass or fur, or other patterns like in this example here, the flag on the top right in the image that is shown here on the slide, or the text on the window. And to address this problem, we propose a method that uses an off-the-shelf vision language model as a perceptual judge to improve current autoencoder training to focus more on human-aligned image compression. And as you can see here on the slide, our method improves the text on the window. And if you look closely, it also improves the pattern on the flag, despite not being actually correct pixel-wise. So instead, our method produces a flag pattern that to us human looks kind of the same. But if you take a very close look, you can see that the white points on the flag are actually not identical, but located in different positions. I'm not sure if you can see this through Zoom, but yeah, you can see this on our webpage later once we upload it. So the question is like, how can we achieve something like this? So let's have a look at this method. So the idea here is that given the original image, we're using a diffusion autoencoder and decode the original image twice using 2 different noise seeds to get a decoding A and a decoding B. And we then prompt a VLM to evaluate which of the 2 decodings is preferred. And based on the response of the VLM, we then use a diffusion DPO to improve the diffusion autoencoder. And in theory, here any reward function could be used to determine the losing and the winning decoding. But in our case, we chosen VLM to do so, which is the novelty of this method. So let's have a look at our method in a bit more detail. So again, given those 2 decodings, A and B, as well as the original image, we prompt the network to analyze those 2 different samples from the AE. And the VLM is then tasked to produce a numerical rating between -5 and 5, indicating whether the reconstruction A or reconstruction B is closer to the original image. And here negative numbers means that A is better, which is the case in this example shown here. And since VLMs are prone to hallucinations, we use the following 3 strategies to make our loss more robust. So first, instead of just feeding in A and B, always in the same order, we also reverse the order of the input images to the VLM. And secondly, we run the VLM for multiple seeds for A and B, and then sum them up to reduce the noisiness of the outputs of the VLM. And then thirdly, I mentioned earlier that we can also use any kind of metric here to determine which of the 2 images is better. So what we did for the third one is that we additionally use an LPIPS metric to determine which reconstruction is more accurate. And if the VLM and the LPIPS agree, we then pass the rating to the diffusion DPO, and otherwise we just discard the sample. And we also ran ablations and tested the LPIPS and the VLM preferences independently. And while using each preference scheme independently improves the results, using both schemes together or like combined results in the best performance. So comparing our method with other competitors, we can see that our method allows us to correctly decode the text, as you can see here. And when we look at the building in the background, we can also see that it improves the high frequency textures of the windows, or like the smaller parts of the windows. And then furthermore, in the second example at the bottom, we can see that our method improves the face reconstruction. As you can see here, if you look at the woman on the right, and as well as the patterns on the wall in the background. And we also evaluated this method quantitatively against multiple competitors on multiple data sets. And most of the methods are trained on varying bits per pixel, which we don't denote here as BPP. So we also trained our method on 2 different BPPs. One model was trained on 0.07 and the other one was trained for 0.21 BPP. And when we look at the numbers, our method actually performs quite poorly on PSNR, as you can see here on the right. So our method is shown as a blue line, and a higher value for PSNR means the results are better. but you can see that our results actually have the lowest and therefore worst numbers. But this is, well, but that's actually, that wasn't really our goal to improve the PSNR here, but we were rather cared about the human perception since this is what we wanted. And to get a better sense for this, we then also ran a user study and computed an ELO score for all the methods. And as we can see here, our method actually performs quite well on the MS Coco and the Click 2020 dataset. However, our method actually underperforms compared to the PO-ELIC method on the Click 2022 dataset. And this is a little bit unfortunate, but here it's actually hard to say why this is the case, because PO-ELIC didn't actually release their code, and the Click 2022 dataset also only contained 30 images, which then can also potentially lead to noisy results. But then looking at other perceptual metrics like FID Dino, and the LPIP score, we can see that our method actually performs quite well across the board. Okay, so this brings us to the end of our VAE detour. And while this wasn't really directly focusing on 3D generation, I would be very interested in seeing how we can use VLM post-training similar to what I talked about here for 3D related tasks. And with that being said, let's hop back to generative 3D again. So earlier I presented both 3D, which was a method to generate 3D scenes in a feed-forward manner, given 2D generated images. And so far, we've talked about a lot of 3D generation of 3D generation of content. But an important factor for content creation is also to allow for fine-grained control of the outputs. And one such control is lighting. So in the next chapter, we will talk about how to enable light control for generative 3D models. And we address this in this task in our method called Roger. And here, given post images in a target illumination, the goal is to produce a 3D-related model under novel illumination. And to achieve this, we train a multi-view relighting model similar to the multi-view models for Cat3D and Bolt3D, but this time for relighting. And the difference here is that the input is not only a set of images and their corresponding poses, but also has a light condition. And we then train this model to produce relit versions of the input views for each available light from 1 to light m. And the goal of this multi-view model is to produce a dataset of n by m relit images that then can be used as a dataset for a light-conditioned nerve optimization. And the goal is to relight an object under lots of different illuminations so that we can then train a nerve to condition on a target light. So here, think about a light stage where we turn on and off arbitrary lights. And the idea is that if we cover a diverse enough set of different illuminations, the nerve should be able to generalize to unseen target illuminations. So let's start first with a standard nerve setup where we condition the nerve for every pose, here, so for every pose I, and we compute a rendering loss on the image corresponding to the input pose. And to train a light conditioned nerve, the task is to encode the input lights so we can also feed in an input light as an additional conditioning. And then the next question is, well, how do you pick the right representation to encode the lighting, because this is non-trivial. And in our case, we opted for an environment representation, and we feed this environment through a transformer encoder to get a light embedding. And while in theory this should be sufficient to represent the lighting, we found that the encoder wasn't powerful enough to always take care of all the specular regions. So to address this issue, we additionally created a specular embedding that explicitly encodes the incident light from the specular reflection direction. And instead of only sampling a single value from the environment map at the reflection direction, we sample locally around the env map to handle different roughness values. And the way we do this is by pre-blurring the env map so that we can then sample a single location as embedding. So once we train this nerve, we can then condition it on any target lighting to relight the 3D model. And on this slide here, we show that different target lightings for a given source lighting. And we can see that our model faithfully recovers specular highlights, while competitor methods struggle to do so. And the competitor methods either misses to fully produce the specular highlight, as we can see in the top row, or it overcompensates for the specular highlight, as you can see on the bottom row. So as you can see, this method fits nicely into our generative 3D setup and extended the number of controls. So what we learned from this type of method setup, where we have a generative part and then a 3D distillation part, is that we can see that the 3D part will only ever be as good as the 2D generation part, as the 3D part is dependent on good generations. So if you remember Richard Sutton, that says, assume abundance of data and compute and limit the inductive bias, we should assume that 2D generative methods will scale, whereas 3D models will not scale. But the 3D models are cost and time efficient. And one work that demonstrates the dependence of a strong 2D generator is one of our works called CubeDiff. And in CubeDiff, we address the task of 360 panorama generation given text or a single image. However, 360 panorama data is actually quite limited. So the task is, how can we scale a method to generate 360 panorama images despite a limited amount of data? And the key idea here is that we can treat 360 panorama images as cube map with 6 faces. So treating them as 6 different sides of a cube means that each individual image is a perspective image that belongs to the distribution of most images that exist on the internet. And now if we stack up all of those 6 images along their channel dimension, we can train a 360 panorama generation model using the same architecture as a standard 2D diffusion model. And the way we do this is by feeding the stack of those images to a 2D decoder, and then almost entirely we are reusing the architecture of existing 2D models. And in our case here, we're just using a pre-trained stable diffusion model. And since such a pre-trained model is already capable of producing the distribution of all the perspective images, we don't actually need to further train the existing layers of the model, so we keep those frozen. However, what is important here, what the model is not capable of doing yet, is to reason about the 3D layout of this cube map and how those 6 input images belong together. So what we did is we added tension layers between all the residual blocks that are then trained to learn the spatial relationship of the different images contained in this cube map. And since the task of understanding the relationships between the 6 images is significantly easier than learning the entire distribution of images, a small data set of panorama images in the order of the magnitude of tenths of thousands of images was enough to train the generative 360 panorama model. And although our panorama dataset, as I just mentioned, is limited, and although this panorama dataset is actually limited to natural images, our model can generate outputs beyond this distribution, as you can see here. And this is possible because we freeze the foundation, the 2D foundation model or the 2D foundation network, which retains its ability to generate any kind of perspective image. And yeah, this example here just illustrates the out of distribution capability. So getting back to the lesson, overall it seems quite untrivial to train 3D methods to be independent of 2D models, just due to the pure lack of 3D data. So should we be focusing on making 2D models more cost efficient and speed efficient? And our friends at World Labs have been working on an interactive 3D model that is capable of real-time next frame prediction on a single GPU. And while the results are not really perfect, it seems to be a very promising direction. So this gets us to answering the question, why is 3D still important for content generation? while 2D methods are already producing highly realistic videos and have already shown interactive capabilities such as camera control, we do not yet have a full and precise control over them yet. And more importantly, though, these models cannot really be served currently, so we still require 3D distillation for serving at the moment. And whether that will change in the future, well, I guess we will see. And with that, I would like to conclude and thank you for listening, and also say a big thanks to all of my collaborators.